once again here in this channel, Her Majesty Easy World Science Channel. Thanks for returning. If you're a new visitor, don't forget to subscribe. I cannot do without you. Please share, like, and comment. So today I'll be analyzing two salts separately, and actually I'll still mix them together. The two salts I'll be analyzing, I'll be taking a look at this salt here, lead nitrate. I'll take a look at the salt. Then here is the same salt. This is calcium chloride. This looks so local. Then I use this black leather here to make sure that this is sealed to prevent air and water vapor from moving in. This one is not sealed. Calcium chloride is a strong deliquescent and it absorbs moisture to form a solution. That's why it is also used as a drying agent, but under controlled condition. You can see this one, I don't seal it with this black leather, it has absorbed enough moisture, though this is still sealed, but it's now a solution in it. Then this one is still, you can see, solid. So this my seal is working. The leather here is to prevent air and water vapor from moving into it, to keep it solid, because it has high affinity for water vapor in the air. So that's just very well. Now these two salts are the same. I'll be analyzing the lead nitrate solution and this calcium chloride solution. Over here I have gotten their solutions, their strengths about 0.5 and 0.6, nearly, let's take 0.6 mole for each. So this one is E for calcium chloride, about 15 cm cube of the solution of it, about 0.5 moles. And this one is still lead nitrate. This is the reagent bottle or specimen bottle. So I'll be analyzing them separately and I will also mix them. Then first, you should know that these two salts are actually soluble. Lead nitrate, which I have over here, is soluble. Remember, all nitrates are soluble in water, no exception. So if they ask you any soluble salt of an unknown element, or any soluble salt of an element that you don't know, you just call that element and put it in nitrate. For example, if they tell you any soluble salt of calcium, you say calcium nitrate. So all triazole are soluble. Then here is also calcium chloride. Most chlorides are soluble except lead 2 chloride, silver chloride, and some other one like copper 1 chloride, mercury chloride, mercury 1, they don't dissolve, but most chlorides are soluble. So these are two soluble salts. Then when you mix the two, there will be a double decomposition, meaning there will be a formation of an insoluble salt. Remember, double decomposition is a common approach used in the preparation of insoluble salts. So if I mix these two clear solutions, there will be white precipitate forming an insoluble lead 2 chloride. So just know that if you are asked to mix the two, there will be double decomposition. So you can use one to analyze the other. Understand what I'm saying here? So then let's take a look at what we require in this analysis. First, I have my litmus paper. We might be testing them with litmus. You have glass rod to stir when needed. Then the filtration apparatus. Here is my filtration funnel, Workman filter paper. Here is the test tube where I filter into. Then the reagents, I need sodium hydroxide, aqueous. I need ammonium solution, aqueous ammonia or ammonium hydroxide. Then there will be also a need to use silver nitrate, depending, silver triazole 95 solution, aqueous. Then you might also be told we might be needing also this potassium iodide solution. It is also necessary and also useful in this analysis. Okay, so then my heating apparatus, here is my Bunsen burner. Then I have my test tube holder, my modified boiling tool, which I will use now for boiling if the need be. So we don't require much things in this analysis. First, like I said earlier, you might be faced with testing the solutions of the calcium chloride and the lead 2 triazole 95 with litmus paper. First, let us theorize what we are expected to have here. When we are asked to test a solution of a salt with litmus, they are just teaching you nothing but salt hydrolysis. Salt hydrolysis. Just some salts, when dissolved in water, hydrolyzes to give an acidic solution, but they are normal salts. But some dissolve in water to give alkaline solution, but they are naturally normal salts. They are not just actually basic salt or acid salt. We are talking about normal salt. So lead nitrate is a normal salt, but when dissolved in water, it dissociates and actually hydrolyzes to give you lead 2 ion and nitrate 5 ion, trioxonitrate ion. Just to know that lead 2 trioxonitrate is a salt of weak base and a strong acid. How do you know the base that formed the salt? Just remove the anion, which is nitrate 5 ion, that's the NO3, then put OH. So what you have now is lead 2 hydroxide, Pb bracket OH bracket 2. So lead 2 hydroxide definitely is insoluble and is a weak base. Then, for you to know the acid, remove the cation, then remove the cation in the salt sample, replace it with hydrogen. So in the salt, that's lead nitrate, Pb bracket NO3 bracket 2. Remove the lead and put H. So what we have is HNO3. So lead nitrate is a salt formed from lead 2 hydroxide and trioxonitrate 5 acid. So trioxonitrate 5 acid is a strong acid, while lead 2 hydroxide is a weak base. So a salt of weak base and strong acid hydrolyzes in water to give an acidic solution. So from my analysis, it shows that lead 2 trioxonitrate 5 will have effect on litmus. Probably it is going to turn red litmus paper blue because it's going to behave as an acidic solution. It will have effect on actually blue litmus paper. Blue litmus paper is going to turn blue litmus paper red because it's an acidic solution. Not that it's an acid, but it hydrolyzes to form acidic solution. Then, theoretically, calcium chloride should be, it's probably going to be a neutral something because the acid here is HCl. Remove the calcium. I told you if you want to know the acid, we are talking about calcium chloride. Remove the metal, which is calcium. Put hydrogen. You have HCl. Don't worry about the two. Just know there is no acid written HCl2, so the only possible acid there is HCl. Then remove the chloride ion and put OH. What you have is calcium hydroxide. Calcium hydroxide is a bit intermediate. It dissolves, but not fully well. It's not all that strong base, but it's not all that too weak. So we might be expecting something that might not have any effect on litmus paper because salts of strong acid and strong bases do not hydrolyze. When you dissolve them in water, they have no effect on litmus paper. And so do salts of weak acid and weak base also behave. They don't hydrolyze. The ones that hydrolyze are when the salt is formed from a weak acid and a strong base, or vice versa. But when both are strong, no hydrolysis. But when both are weak, no hydrolysis. So first, I'll start by testing the two solutions of calcium chloride and lead nitrate with litmus paper. Here is my litmus paper. Here is actually blue litmus paper. Okay. This lead nitrate solution is blue. Okay, it is slightly turning it. Yeah, it turns blue litmus paper red, of course, as I predicted, because it hydrolyzes to form acidic solution. So that's it. Okay. Remember that phenolphthalein will also be colorless in lead nitrate. Why? Because it's also acidic solution, and phenolphthalein is also colorless in acids. So then, if you use any other indicator, as you can see, my hands are actually, yeah, this is very obvious now. Yes, yeah. It turns blue litmus paper red. You can see the blue remaining, then the red aspect of it. Okay, yeah. So lead nitrate turns blue litmus paper red. Your inference should be L, or whatever you might decide to label it, is acidic. Remember the test is test L with litmus. Observation, it turns blue litmus paper red. Your inference should be, that's your conclusion, should be that C or L is an acidic solution. So we come over here for calcium chloride, supposed to actually behave as an acidic solution also. Let's check because the HCl there. It's not showing any obvious color change. No obvious color change on blue litmus. Then going with red litmus. Remember, when a solution turns blue red, no need of checking it with red again. That's why I did not do it to that of lead nitrate. I didn't use red because since it has affected blue, it won't affect red again. But this one that did not affect blue, let's check if it can affect red. Okay, so no action. So it shows that this solution E is neutral to litmus. Okay, then the next thing we might face is each of the solutions E and L, you might be told to divide into 3 or 2 portions. So here are my test tubes, of course. So I'm going to use this for the division into the portions. So this is my lead nitrate. Okay, it shows this not clear. To wash the test tube. Because my hands are contaminated already. So wash my hands. Okay. Collecting first portion from L, that's lead nitrate. For detailed analysis on lead and lead nitrate, watch my video here on test for lead 2 ion. The video here on this channel has the details on how you can test for lead 2 ions, and what I used in that video is actually lead 2 2095. Remember that Some Majesty's World Science channel is not only meant for exams. This is science channel. Science is not meant for only exams. Rather, exams are tests that you do to get you qualified towards the application of science. Please, my co-Africans, let's focus on science more than we focus on science, on the certificates and the exams. Let's focus on science, the application. That's what's going to save our nation, please. Endeavor to watch most of my videos here. Some of you only visit when this particular video is titled an exam. But as you can see, I've referred you to a video that has been existing here on this channel. But maybe you don't have time to click or search. Why? Because it's not written any kind of JAMB, WAEC, NECO, or any exam. No. Please, this channel is science channel and is wide. It is covering all the aspects of science. With time, more and more will be coming. Check even human anatomy, science tricks and hacks. There are many videos here, up to 120 of them, not only for exams. Then check powerful tutorials. Then don't forget to also place order for your chemicals. I sell and supply all these. So lead nitrates, your calcium chloride, and I'll also help you in quality control. The advantage of buying from Some Majesty's World Science channel is that you are assured of the quality of what you're buying. You're buying from the chemist himself, who knows what he is selling to you. When you go to the market, the person selling might not even know what he's selling. He sells according to the label. But I will analyze and give you the pure sample for high quality. So call the number there on the screen to place your order. Now, back to what we're saying in the analysis. This is my first portion of lead nitrate. It might be called actually L or whatever letter you want to call it. So you might be told to add to the first portion to add sodium hydroxide in drops, then in excess. So this is my sodium hydroxide. I'm going to add it to this first portion of L, that is first portion of lead nitrate. In drops, you see, in drops, there is white chalky precipitate or white powdery precipitate. Then in excess, let's see what happens. So in excess, it dissolves. See it, precipitate dissolves to form a clear solution. And when this happens and you are using sodium hydroxide, test means first portion of L, which is lead nitrate, because sodium hydroxide drops in excess. Observation, white chalky precipitate formed in drops, which dissolved in excess of the sodium hydroxide, or white powdery precipitate formed, which remains soluble in excess, or which dissolves in excess to form a clear solution. Your inference should be lead 2 ion zinc 2 ion or aluminium ion suspected, but in real sense, it is only lead that is powdery among these three. But when anything forms white powdery precipitate with sodium hydroxide in drops, you suspect lead aluminium or lead aluminium, zinc, and calcium. Those four also forms white precipitate with sodium hydroxide in drops, but in excess, it is only lead, aluminium, or zinc that will dissolve. But in excess, calcium will not dissolve. But thank God we have that E is calcium. So we'll be comparing it now. I'll be running this thing collectively, analyzing these two samples collectively. Remember what I've just done now. I've given you the test, the observation. Your inference has also been stated clearly. Test is first portion of lead nitrate, maybe letter L plus sodium hydroxide in drops till excess. Observation, white powdery precipitate or white chalky precipitate formed in drops. Precipitate dissolved in excess of sodium hydroxide to form a clear solution. Inference, lead 2 ion, aluminium ion or zinc ion suspected or likely. But I told you one thing now, I'm repeating. In real sense, because it's chalky, I've been analyzing, I'm experienced in this. Because it's chalky, there is no need of even calling aluminium or zinc. Zinc is very much gelatinous. But let's assume we didn't take note of the nature of the precipitate until the exam bodies take note that they shouldn't be including zinc or aluminium when you report chalky precipitate. But maybe when I go through some of the marking scheme like that of WAEC, they still give mark for those that included zinc or aluminium, but it is chalky. So that's not science, but with time we will come to perfection. Okay? Then I say let me collectively be analyzing them. This is E, which is calcium chloride. I'm collecting a sample of it, trying to do the same thing I did with sodium hydroxide. So this first portion of calcium chloride. First portion of E, I'm adding sodium hydroxide in drops. In drops, there is white powdery precipitate. The precipitate is also white powdery. Let's see what happens in excess. You see, in excess, the precipitate persists in excess. You see the difference between lead and aluminium. Sorry, lead and calcium ion, sorry. So both forms white powdery precipitate with sodium hydroxide in drops. Remember, in analysis, if you add in drops, you are required to notice the color and the nature of the precipitate formed. And that's why I say white powder, color white, nature powder. Then in excess, you are checking if the precipitate will dissolve or if it will persist. So in this case, you can see this one has dissolved clearly and this one is persisting. So though below here you might be looking at if it is persisting, but it has dissolved. If you shake well, find out that the solution will become uniformly clear. It's showing that I have not added excess. If I add more base, see, it will be very, very clear. So no need of telling you that this is dissolving and the other one is persisting. Okay, so that's it. So if you are told to do this with specimen E or solution E, whatever they call it, mean calcium chloride, if you add sodium hydroxide in drops to this, there will be white powdery precipitate. If you add to lead nitrate, there will also be white powdery precipitate. But in excess, calcium will persist, lead will dissolve. Which other ion did I tell you will also dissolve in excess sodium hydroxide? They include aluminium, zinc, in addition to lead. Why will these three dissolve, but calcium will not dissolve? Because aluminium, lead, and zinc are amphoteric metals, meaning they have basic and acidic properties, and their hydroxides and oxides also have such properties. That's why they dissolved here to form a complex ion. But calcium is not amphoteric. The hydroxide is never amphoteric, and the oxide is never amphoteric. So it cannot dissolve in excess sodium hydroxide. So that's the explanation in this case. Okay. Secondly, you might be told to repeat exactly what I did now with aqueous ammonia in each case. So let us see what happens when I repeat the same process using aqueous ammonia. This is my aqueous ammonia. I want to rinse the dropper, possibly use more than one. Okay, Okay, I have my two new sets of test tubes. Remember to wash the test tubes well to avoid contamination. Use your test tube brush. I have one over there, but I washed it before this video before I started. So I want to collect samples of lead nitrate and calcium chloride and apply the same thing I did with so this my E, which is calcium chloride. I'm testing for calcium ion. So repeating the same process we saw a few minutes ago, but now using aqueous ammonia, no longer aqueous hydroxide. This my lead with ammonia. There is still white chalky precipitate. Then with calcium and ammonia, there is slight turbidity in drops. Slight turbidity. So calcium ion forms slight turbidity with aqueous ammonia. Unlike white chalky precipitate obtained when we use sodium hydroxide against calcium. But with sodium, aqueous ammonia, it's just slight turbidity. But then lead also forms white powdery precipitate, just like it did with sodium hydroxide. So with lead in drops, lead forms white powdery precipitate with sodium hydroxide and also with aqueous ammonia. Then in excess, the difference is clear. When we add this in excess, remember I'm adding to the lead nitrate sample. In excess, I have to fill this. It shows that it's persisting, it's not dissolving at all. So in that of it will still be unclear, it will still be turbid. So the turbidity remains. So both lead and calcium don't dissolve in excess aqueous ammonia. So this, when we are asked to add ammonia to either sample L or E or sample A or B, meaning A is lead A is calcium chloride, B should be lead nitrate, depending on whatever you want to name it. Just know that when you add aqueous ammonia to lead nitrate, there will be white powdery precipitate in drops, which will persist in excess. It will not dissolve. This one was the result we got with sodium hydroxide. So it dissolved in sodium hydroxide. Lead dissolves in excess sodium hydroxide. The same lead persists in excess aqueous ammonia. Reason: lead is not a complex. Lead is not a transition metal and doesn't form complex ion with ammonia, unlike zinc and aluminium. Meaning zinc will dissolve in excess aqueous ammonia, but aluminium and lead will not dissolve. Just watch that video, the test for cations. I specified them. There is even a video on tests for mostly all the cations you will encounter. And there is also separate videos on each one. Test for aluminium, test for lead, test for calcium. Just endeavor to search those videos here at Her Majesty Easy World Science channel. Then don't forget to share my videos. Thanks for being there. So we are done with the aqueous ammonia. So you should also learn how to test for chloride ion, because the calcium chloride have chloride ion. In testing for chloride ion, you either use lead nitrate or silver nitrate. So it's possible that L will be used to detect the presence of chloride in E. Calcium chloride might be detected using the L. How they may do this is that they just tell you, you might be told, or you can do it yourself, get first portion or second portion of this. That second portion of E is actually unknown. Say it's unknown here. But I'm calling it name so that you know that this is calcium chloride. I'm teaching you how to test for chloride ion. You can use lead nitrate to test for chloride ion by this thing I'm showing you now. If you add lead nitrate to any soluble chloride, there will be double the composition as I told you earlier. So you might also be told to measure small part of L and add to a measured volume of E. That is trying to make double the composition. So if I add, there will be white powdery precipitate, which when I heat this or warm this, either way, when I heat it, this precipitate will disappear on warming and reappear on cooling. So what does it mean? You have to confirm chloride ion. But for them to use lead nitrate to test for E, they must mention that this is lead nitrate, so which might not be possible. They might take the two as unknown. When these two will be mixed as two unknowns, I'll tell you what to do. But here I'm just teaching you that lead nitrate can be used to detect chloride ion. It involves adding lead nitrate to the unknown sample, the formation of white powdery precipitate which dissolves on heating and reappears on cooling, indicates or confirms chloride ion. How? Lead 2 chloride is insoluble in cold water but soluble in hot water. So on warming, you are making the water hot, and that's why the precipitate will disappear, because it dissolves in hot water but not in cold water, as you can see now. So I mixed both L and E. Now I'm going to warm. It's expected that the precipitate will disappear on warming, or on heating actually, and then if I keep it for a long time, the precipitate will still return back. Okay, this is my boiling burner. I guess this is not working. Okay, I'm now heating. Shake. See, on heating, there is no more precipitate. So the precipitate dissolves on heating. If I allow it to cool again or put it in a freezer now, a refrigerator, it will come back again. The precipitate will come back. So whenever you are asked to add lead nitrate to an unknown sample, the formation of white powdery precipitate, which disappears on heating and reappears on cooling, confirms chloride ion. So the test might be sample E plus lead nitrate in just lead nitrate here, you don't need to add in excess of drops, then followed by heating. The observation is white powdery or white chalky precipitate, which disappears on heating and reappears on cooling. So remember, this is the same result you will get when you are asked to mix solutions L and E, that's solutions calcium chloride and solution lead 2 triazonitrile. There will be double decomposition, and insoluble particle formed is called lead 2 chloride, and it is soluble in hot water but insoluble in cold water. So proceed to the next possible thing. Oh, sorry. I think I'm done with heating. Okay, the lead nitrate, you might also confirm the presence of lead, since lead and aluminium behave similar with sodium hydroxide and aqueous ammonia. Lead and aluminium, both of them will give you similar results in terms of color of precipitate and solubility. Lead forms white powdery precipitate which dissolves in excess sodium hydroxide. Aluminium also do the same thing. Zinc also do the same thing. But with aqueous ammonia, zinc will dissolve in excess, but aluminium and lead will not dissolve. So, which means with sodium hydroxide and aqueous ammonia, you cannot clearly distinguish between lead and aluminium, since both of them will be soluble in excess sodium hydroxide and remain insoluble in excess aqueous ammonia. So, what do? There should be another step to distinguish the two. And there are three things that we use to distinguish between lead and aluminium, and these things are conc HCl, lead 2 chloride, conc HCl, then potassium iodide, and hydrogen sulfide. Just watch the video on distinguishing between aluminium and lead here on this channel. You understand what I'm saying? So, but here I'll just show you the entertaining reaction between potassium iodide and lead 2 chloride. So, potassium iodide and lead 2 ion. In the presence of lead 2 ion, if you add potassium iodide, what I have here is a potassium iodide solution, there will be a yellow precipitate of lead 2 iodide. Is an entertaining double decomposition reaction. So in that case, you might be told to add either HCl to this sample of lead nitrate. There will be white powdered precipitate if you add HCl, but if there is aluminium, there won't be any white precipitate. So if all things being equal, see, that's it. I added potassium iodide and it formed a yellow precipitate of a lead 2 iodide. But aluminium will have no color. If this compound is aluminium and add potassium iodide, there won't be any visible reaction. There won't be any double decomposition. So that's it for distinguishing between a lead 2 ion and aluminium ion. So in this analysis, you must be specific to confirm. So this has confirmed that my sample L is lead, no longer aluminium. Let's assume I wasn't observant enough to know the nature of their precipitate, because since they tend to behave the same way with sodium hydroxide and aqueous ammonia, I have to use potassium iodide or hydrochloric acid to distinguish. The result with hydrochloric acid is what we just exactly saw here. The hydrochloric acid is just to introduce the chloride ion, which in the presence of lead 2 will form insoluble lead 2 chloride, but in the presence of aluminium will form soluble aluminium chloride. So there won't be any precipitate when you add HCl to aluminium salt, but there will be precipitates when you add HCl to lead 2 salt, and that precipitate is lead 2 chloride, simple, and which will disappear on heating and reappear on cooling. So that's it. Then one might also be told to do this, to test for chloride ion using silver nitrate. So test for chloride ions using silver nitrate. We will use the same pattern. I have to discard some of this. With silver nitrate, you just add silver nitrate and followed by excess aqueous ammonia. That will confirm presence or absence of chloride ion. With lead nitrate, you heat and allow to cool, but with silver nitrate, you don't need to heat, rather you need to follow it up by adding excess aqueous ammonia. Okay, so here is, I have to also wash my hands. This is the chloride ion. I've introduced it there. Then this is silver nitrate. There will be white powdered precipitate, as you can see already, but the precipitates will dissolve in excess aqueous ammonia. My ammonia is almost exhausted. Okay, so you can see the precipitate is dissolving, supposed to give us a very clear solution. I think the ammonia I have here is almost finished. This is another aqueous ammonia. Let me believe this is gone. Okay. This is the okay, there is much of the ion. That's the problem. So it dissolves in excess aqueous ammonia. So this is giving us light turbidity. Maybe the excess calcium chloride remaining is still showing some reaction with aqueous ammonia. Of course, that's what is just happening here. If not, there's supposed to be a very clear solution. Okay. Now, the next possible thing you might be asked to do is to mix solution, or the last portion of solutions A and B, or solutions E and L, C and D, no matter what they call it, but just to mix the two solutions, that's lead nitrate and calcium chloride. I told you if you do this, what's happening is actually double decomposition. So mix some first portion of L with first portion of E, then filter, keep both the filtrates and the residue. So if that happens, as you can see here, it means that there will be exchange of radical. The residue will be lead-2 chloride, while the filtrate will now be calcium nitrate, because there will be exchange of radical. The nitrate in the lead will go to the calcium in the calcium chloride, while the chlorine in the calcium chloride will go to the lead in lead nitrate. So there will be white precipitate. So you might be told to do what now? To filter, keep both the residue and the filtrate. Okay. I want to filter this. I have my Workman filter paper here. So if you are told to do this, you just report white residue and colorless filtrate. So your inference is that soluble and insoluble salts are formed when you mix the two, or you can write double decomposition has taken place, because if they provided E as a clear solution and L as clear solution, and mixing the two, you have white precipitate. You are correct. The report double decomposition has taken place. In your inference, double decomposition occurs. So I'm filtering, and I'm giving you the observation and the inference. You can see the filtrate is clear filtrate. And then white residue. Okay, see the filtration is complete. So here the colorless filtrate, and here is the white residue. If you are told to keep the two, you still go back and carry out the test. Here is calcium nitrate. You'll be asked to add sodium hydroxide in drops. Remember what I told you when you use sodium hydroxide in testing for calcium ion. So you might be told to divide this into 3 portions. The first one you add sodium hydroxide in drops. Then the second one you might be told to add aqueous ammonia in drops. Then you also learn, in case, just how to test for nitrate 5 ion. You can also learn how to test for nitrate 5 ion using brown ring test. Check it out here on this channel, Her Majesty's World Science, and I have these experiments already waiting for you here on this channel. So what might be told to confirm here, this filtrate now is calcium nitrate and this residue is lead-2 chloride, and we started from calcium chloride and lead nitrate. There will be exchange of radicals, such that what we have now is calcium nitrate, and here is our lead-2 chloride. So that's it for this particular mixture of salt, or these two salts being analyzed tentatively or collectively. Thanks for being there. Please subscribe, share and like my videos. Expand the easy world of science. Bye for now. I hope to see you soonest.